Hello everyone, today let's take a look at QP167 where we're looking at some discrete order stats. So basically we have a box with n balls. The balls are labeled 1 through n and you're going to draw m of those balls uniformly at random without replacement. So we let m sub min and basically m sub max denote the minimum and maximum labels among the m balls. So now we need to answer these three questions here. In part A we find the expected value of the minimum ball out of those m. In part B we find the expected value of the maximum. And in part C we're just going to find the expected value of any order statistic, right? The rth order statistic in general. So for part A, this should be very similar. Should remind you exactly of QP149, which is the question just before this on the roadmap, right? So if we want to find the expected value of the minimum, just like we were in that question, right? We could iterate through every single possible minimum value and the probability that it's the minimum, right? Using the definition of expected value, but it's just going to be a lot easier to use the tail sum. And for the tail sum formula, we're just going to be summing up from k equals 0 all the way up to infinity, basically the probability that minimum is greater than that k value, right? And again, this is going to be much easier than the definition of the expected value formula, which would have us going from k equals 0 to n, and then we'd be taking k times the probability that the minimum was equal to k, right? But this right here was going to be basically a hypergeometric type of sum that we're doing, so we do not want this k out front, which is why the tail sum is much simpler, because we don't have that k out front. So let's do it with this tail sum way, and let's just start working through a few examples. So what is the probability that the minimum is greater than 0, first of all? Well, we have a box here with n different balls. We're drawing m of them, right? So the probability the minimum's greater than 0, well, the balls are labeled 1 through n. So if you draw any balls, it's going to be greater than 0. So this is a 100% probability. Now let's do the probability that the minimum is greater than 1, which only happens if of our m balls, we don't have the ball labeled 1 as one of those balls. And the probability of that happening, well, in total, we have n choose m different ways to choose these balls. And of these different draws, how many of them do not include 1? Well, if we just exclude 1, then we're going to have n minus 1 different balls that we could choose m from, right? So n minus 1 choose m on the top. This is going to be our probability. Now, what's the probability the minimum is greater than 2? Again, we have n choose m different ways to choose these balls. Now we do not want 1 or 2 to be among those options, right? So now we have n minus 2 remaining balls that we need to choose m from. So this is going to be our probability right here. And now you can see the pattern. The probability that the minimum is greater than any value k is just going to be n minus k choose m, the number of ways to choose the balls that exclude the first k options, right? And then that's going to be divided by the total number of ways to choose the balls in general, which is just n choose m. And that's going to be true for all these k values from 0 all the way up to n, right? Because if I have the probability that the minimum is greater than n, well, that's obviously just going to be 0. And for any number bigger than n, right? Because we only have balls labeled up to n, so there's no way that we could get a minimum that is greater than n, right? So we do not need to do this sum to infinity. We just have to do it to n because, again, any number past n or equal to n, when we plug it in for k here, will just give us a probability of 0. So now that we know this pattern, let's just plug in this formula right here in for this value. So when I do that, this is what our new formula looks like. We're multiplying this sum right here by 1 over n choose m, right? That was our bottom term here. It's going to be a constant relative to this iterator, so we can just pull it out, right? And now we're just summing up over this right here, which we need to calculate. So if we look at what this sum right here is just going to be equal to, if we just write out a few terms, it's going to be equal to n choose m for our first term, and then k is going to iterate to 1. So we're going to have n minus 1 choose m, and then we're going to have n minus 2 choose m, etc., all the way up to basically n minus n choose m, right? That's going to be our final term. Now you'll see if m was equal to 5, right, we'd have 0 choose 5 here, right? The term before, it would be 1 choose 5. The term before would be 2 choose 5. Those would all be 0, right? So the only terms that would contribute would basically be when m is at least as great as this term right here. So because based on that value of m, these later terms are going to be equal to 0, we're basically going to stop the contributions that are non-zero to this sum at m choose m. So now this is a sum that we know the value of, right, from QP135. This is going to be the hockey stick identity. We know that that's just going to be equal to n plus 1 choose m plus 1, right? So that's the value of this orange sum right here. It's n plus 1 choose m plus 1, and then we still have this constant factor out front, which was n choose m. So that's just going to be our final answer right here. But we can actually simplify this pretty greatly if we just expand the definition of basically binomial coefficient. So when you expand both binomial coefficients, this is what you get on the top, and this is what you get on the bottom, obviously. This one right here will simplify. You can see that the ones are going to cancel, and this is just going to simplify down to n minus m factorial. You can see we get a lot of cancellations. We can just multiply this by the reciprocal. The reciprocal of that was just m factorial n 1 minus m factorial divided by n factorial. These are going to cancel right here, and then we're going to have n plus 1 on the top. This is going to cancel with the first n terms of this, and then this will cancel right here with the first m terms of this. So that's just going to leave us with n plus 1 divided by m plus 1, which will be our most simplified final answer. So for example, if I have 10 balls and I'm drawing 2 of them, well then my expected value of my minimum will just be 11 divided by 3 when we plug in 10 for n and 2 for m. And then one quick sanity check you could do is if, let's say, we have n equals 10 and m also equal to 10, so we're drawing every single ball, then we would expect the minimum to be 1, right? And that's exactly what we get, because we'll just get 11 on 11, which is equal to 1. So that's going to make sense. That's the answer for part A, n plus 1 divided by m plus 1. And now let's go on to part B, which should be relatively similar of a strategy. We're trying to find the expected value of the maximum now. Again, in order to not have that k out in front, tail sum is going to make it a lot easier. So we'll take k equals 0 to infinity of the probability that this maximum is going to be greater than k. Now again, we can just do a few examples. What's the probability that the maximum is going to be greater than 0? Well, that's going to be 100% for the same reasons as before. Now the probability the max is greater than 1 is just going to be most simply thought of as 1 minus the probability that the maximum is less than or equal to 1. And that probability is just going to be equal to basically 1 choose m divided by n choose m, right? That's because in order for the maximum to be equal to 1, we basically need m to be equal to 1. We only need to draw one card, and of that one card that we draw, it has to be 1. You can see this makes sense because if m is greater than 1, right, if it's like 2 or something, then we're going to have 1 choose 2, which is going to be 0, right? All of these binomial coefficients are 0 if this number on the bottom is greater than the number on the top. So only when m equals 1 does this evaluate to 1 on the top here, and then we'll have n on the bottom here. So you can see we have a 1 out of n chance in that situation, right? So that makes sense. Then you can keep on going like this, but you'll find the pattern pretty easily. The probability that the maximum is greater than some value k is just going to be 1 minus the probability that the maximum is less than or equal to that value k. So 1 minus basically k choose m divided by n choose m. And then again, this pattern is going to be true up to when k equals n minus 1, because if k was equal to n, the probability that the maximum is greater than n would be 0, right? And any term greater than n as well. So the last non-zero term that we will need here is going to be n minus 1. So again, let me plug in this formula that we found into our equation up here. Now this is another pretty simple sum to evaluate when we know the hockey stick identity, right? First of all, this term right here, when we sum that up, it's just going to be equal to n because we're going from 0 to n minus 1. That's n times that we're summing up this 1 here. And then for this next part that we're summing up, you can see I did it over here. We're basically pulling out this constant factor. It's constant with respect to the iterator, and now we can just use the hockey stick identity on this. The first non-zero terms in this sum right here are going to be m choose m. When k iterates to m, we're going to have basically m plus 1 choose m. We're going to keep on going all the way up to our final term of n minus 1 choose m. And by hockey stick identity, that sum right there is just going to be equal to n choose m plus 1 in this case. So note that you could have taken this sum up to n instead of n plus 1, and then we'd have basically n plus 1 here instead of an n, and then we'd have n plus 1 choose m plus 1 for this term right here, and it would evaluate to the same thing at the end. I know in the first part I did it to n, and this one I did it to n minus 1, but it really doesn't matter. So then this whole thing right here, we're going to have n minus, well, we have n choose m plus 1 divided by n choose m now, like so. Now let me just expand these binomial sums here so we can simplify a little bit. When I expand them and take the reciprocal of the bottom one, this is what I get. You can see we get a lot of cancellations. These n factorials are going to cancel. This one's going to cancel with the first terms of this, and then this one here is going to cancel with the first terms of this. So we're just going to be left with n minus m divided by m plus 1, and then we still have this n minus that in the front. Now if I combine over the common denominator, I'm going to multiply top and bottom here by m plus 1. So we have n times m plus 1 divided by m plus 1. And then on top, we're going to have n times m plus n when I distribute that. Let's combine these over the common denominator of basically m plus 1. This negative is going to distribute to these terms right here. So we're going to have a negative n, and we're going to have a positive m now. Then these n's here are going to cancel, obviously. We're going to have n times m plus m, which we can pull out an m from to simplify, and then we just get this right here. So that's the final answer for part B. It's going to be m times n plus 1 1 divided by m plus 1. So it's almost very similar to this one up here, right? That one was n plus 1 over m plus 1. We just have this extra factor of m that we're multiplying by now. So that right there is the final answer for part B. And now let's go on to part C, which is probably going to be the hardest one, right? Now this part here should be optional, but basically if we want to find the rth order statistic, so m sub r, that just means if r was 5, then we're trying to find like the 5th biggest number that we expect, right? Or if r is 6, we're trying to find the 6th biggest number that we expect. Now in order to find this, you could use tail sum again, and it's going to be very, very complicated if you do. You're going to have to take a double sum and basically use some variation of Vandermon's identity in solving that way. But a much easier way to think about it will just be in terms of basically like a symmetry argument. And we can do that because we have basically n, the sequence of n integers, right? So it's going to be 1, 2, 3, 4, right? All the way up till n, right? Those are the balls in the box. So we know that if we just choose a random subset of m of them, like for instance, let's say that we get 2, 5, and then maybe we get 7, and then we get maybe 8, and then 13, something like that. So in this case, m was 5 because we chose 5 different balls, right? And they were labeled these numbers here. And then since these all came from the same distribution, right, we just took a random subset of 5 of this sequence of integers right here. We can use this symmetry. We can use the fact that when they're ordered like this, right, the expected number of numbers that we did not choose, right, the numbers between 2 and basically our starting point, which was 1, right? We can call that mu, right? We know that they're all going to be identical, right? Because again, symmetry. So mu, these are all going to have gap lengths of mu. And by gap lengths, I mean the numbers in between. So 6, the numbers that we did not choose. For instance, here, 3 and 4. Numbers between 8 and 13. So 9, 10, 11, and 12, right? They're all going to have the same expected value, right? So there's this equal expected distance by symmetry between all of these different numbers that we choose, essentially. Then if I wanted to calculate the expected value of, let's say, the third order statistic, so r would be equal to 3. In our case, it would be 7 right here. And that's going to be equal to basically by linearity, the sum of all of these gap lengths here plus 1 for this number, plus 1 for this number, and then plus 1 for this number here, right? So the expected length of the rth order statistic is going to be equal to r. In our case, when r was 3, that's basically just counting this 1, 2, and 3, right? And then we're adding on 3 times this expected gap length, which is going to be equal, right? So we're adding on r times mu. And now what is the expected gap length when we choose m numbers? Well, we basically have, if you count m plus 1 different gaps, right? So m plus 1. We know that when we multiply all these gaps by the expected gap length, that should sum up to basically n minus m. That's because we know the sum of all of these gaps right here plus basically the count of all of these numbers right here should be equal to n because we only have n different numbers, right? So basically if we're just summing up all of the gaps, right, all the numbers in between all the numbers that we chose, then that should be equal to n minus all of the numbers that we chose, right? So if we solve for mu here, mu, the expected gap length should be equal to n minus m divided by m plus 1. And then when you plug in that mu for basically this equation right here, right, we're going to get r plus r times n minus m divided by m plus 1. And then we can use the exact same algebra that we did in part B, and then we're going to just be left with, at the end, r times n plus 1, and then that's going to be divided by m plus 1. And that is the expected value of the rth order statistic in this case when we have these balls, right, in this sequence, right, 1, 2, 3, 4, all the way up till n. And you can see that it makes sense because when r is equal to 1, so if r is equal to 1, we're finding the minimum, right? The first order statistic is the minimum. And in that case, we just get r equals 1, so this would just go away and we'd get n plus 1 on m plus 1, which is exactly what we got in part A. Similarly, if we use r equals m, right, so we're looking at the mth order statistic, which is basically the maximum, the expected value of the maximum. When we plug that in here, we get m times n plus 1 on m plus 1, which again is exactly what we got in part B. This is the final answer for part C. It was a complicated question, but it's a good question, right? Because we use hockey stick identity, we're using tail sum, and we're basically having to do this symmetry argument down here.